pleasure today to introduce our speaker, Dr. Jing Yu. She's currently here at Michigan, working on a postdoc with Najmi Oze, who's conveniently out of town. Comes to us from Caltech, where she got her PhD, and she'll be starting a assistant professor position at University of Washington later this year. So I'll let her tell you about her research.
Thank you for the introduction. So at this point, we all know that sustainable energy systems are crucial for addressing climate change. And one of the most fundamental challenges in developing the next generation of sustainable energy systems is that there is uncertainty everywhere. From renewable energy generation to the power grid that transports electricity through, all the way to users and systems that use electricity. For example, it is well known that renewable energy generation is hard to predict because it is intermittent and it comes with a lot of fluctuations. And the type of fluctuation that we encounter can heavily impact the stability of the power grid, which can lead to potential blackouts. Here I'm plotting the wind and solar generation during a typical 2-day period from the Arizona Public Service System. And as you can see here, despite having available historical data, the predicted generation is still quite different from the actual generation. And another type of uncertainty that we often encounter is that the power grid itself is experiencing increasingly large and frequent changes due to the introduction of renewable energy sources. So take as an example the distribution network. So this is the part of the power grid that directly connects to our homes and schools. It not only delivers powers to us, it also takes power from distributed renewable energy resources, such as the solar panels and batteries. Now, we already know that due to a variety of reasons, the distribution network changes its topology throughout the day. For example, it goes through automatic switches to respond to load balancing. And of course, it changes the topology because there's line maintenance. And even sometimes the temperature fluctuations throughout the day can impact significantly the line impedance of the network. And this may be surprising, but a lot of times the grid operators themselves don't even have full information or simply outdated information about their own network topology. And so you would imagine if you're a grid operator and you want to design a control algorithm to stabilize your network, having inaccurate information about your topology is going to pose a significant challenge. And another important challenge is that the end users and systems that use electricity are obviously complex and hard to model accurately. This, of course, not only makes it hard to design energy efficient control algorithms for these systems, it also makes it hard to design intelligent systems that allows us to use these systems to help us make them participate in demand response and to make the overall energy systems more stable. So here's an example. This is what I'm showing here is kind of the heating, ventilating, and AC system or HVAC system of commercial buildings. And so these commercial buildings, HVAC systems actually account for a large proportion of energy consumption globally. And research have shown that using advanced control strategies can really reduce energy consumptions up to like 30%. But of course, to use something like MPC or more intelligent control systems, we need to know its model. But you can already see here, different commercial buildings can have very diverse configurations of its model, and the air and water cooling, heating systems can create very complex thermodynamical interactions. So to kind of build models for each individual buildings is very expensive. Now, one way or another, most of these systems that we do encounter in this pipeline are control dynamical systems. So as control theorists, we obviously want to turn to control theory to make them behave the way we want, and especially to deal with uncertainties. But in its more traditional form, as we all know, that control theory requires us to know more or less accurate information, and we can only deal with some small uncertainty. So in its more traditional form, it's insufficient. And more recently, there's been a huge interest in an emerging approach that tries to combine control theory with machine learning. And this is well motivated by a variety of applications such as robotics. And this approach actually can deal with a lot of new uncertainties, large uncertainties, and sometimes even unknown models in some settings. But I'm going to argue that there's a lot of unique challenges and open problems motivated by sustainable energy systems that we still have to address. Here are some examples. So first of all, a lot of the times we have to learn on the fly and from scratch to control these systems. We simply cannot wait around collecting data, learn a new topology, while a part of our power grid is experiencing unsafe voltage violations. So everything has to be ensured, like we have to ensure safety right off the bat, and we can't assume much knowledge about the unknown system. And moreover, sustainable energy systems are growing in complexity and scale, and they're being more and more integrated into cyber-physical systems. And so there's going to be additional network constraints that we cannot avoid, such as sensing and communication delays. And there's also going to be additional scalability issues that single agent systems or traditional robotics applications simply don't encounter. And of course, they are safety critical. They're potentially the most safety critical applications that one can encounter. And so we want to ensure as much as possible that our control strategies will not fail catastrophically. Now, on the other hand, in a typical control learning setting, it is common to assume some availability of data before we even start learning. For example, it is common to assume that we have a stable lighting controller when even though we have an unknown system. And for the most part, the data collection and learning approach are usually centralized, even for large-scale systems or distributed setting. And while a lot of the algorithms now have safety guarantees, it is still in some limited settings, such as when the disturbances are IID sub-Gaussian. And this type of assumptions, stochasticity assumptions, are simply not enough for energy applications. So for the rest of the talk, I will try to address partially some of these challenges. And to do this, I will introduce an uncertainty set-based approach. I'll start by, I guess, reintroduce a classic control theoretical tool called set membership, and it's a uncertainty set estimation method. And I'll describe to you what it is, why we care about it, and why it's a great tool. And building upon these uncertainty sets, I'll introduce a generic modular learning-based control framework that can unlock a host of new learning-based control algorithms for problems that we couldn't solve before. And the particular problem I want to focus on is learning to stabilize unknown network systems under communication constraints, under adversarial attacks. And finally, we will see how some of these algorithmic ideas come into play in an application in network, in a distribution network with voltage control. So without further ado, I'll dive into the first part of the talk. And I want to start by motivating why we care about uncertainty sets and how we can build control algorithms on top of uncertainty sets. As I mentioned before, many energy systems can be modeled as control dynamical systems. And so here I'm representing them as a typical classic block diagram. In this talk, I will consider state feedback. And I will assume that our dynamical systems are parameterized by a parameter theta star. So I'll refer theta star as the system, as the model, as the parameter interchangeably. And I'm also going to assume there's exogenous disturbances W coming from an admissible disturbance set, which is denoted by calligraphic W. And let's just focus on linear dynamical system here. So the theta star will just be the matrices A and B. So a fundamental control design goal for the system would just to be ensure safety. And by safety, we can, in a generic way, characterize it as a function h of the state and control trajectory X and U, so that the state and control trajectory will always belong to a safety set S for all realization of disturbances coming from the admissible disturbance set. Now, motivated by the uncertainties that I described in the introduction, so more often than not, we would not know exactly what the theta star is. But we could potentially model an uncertainty set P0 that contains what this true system theta star is. So then the problem of ensuring safety for theta star becomes ensuring safety for all the models from this entire uncertainty set P0. And this is basically the principal approach for robust control, right? Now, this approach obviously introduces a trade-off between safety and performance, where we can, of course, start with a model with a large uncertainty set P0 that is guaranteed to contain theta star, so we can guarantee to have safety. But our performance is only going to be as good as the worst case system in this entire set. And of course, we can improve our performance by starting with a small uncertainty set, but we risk having this small uncertainty set not containing the true system and therefore losing the guarantee for safety. And so how do we balance this performance and safety? The answer is kind of obvious, right? We could, instead of sticking with a fixed uncertainty set where we have to trade off safety for performance, we could start with some uncertainty set and start recomputing uncertainty sets with sequentially revealed online data as we control it and try to shrink it while still guaranteeing that our theta star is always in the uncertainty set. So problem and solution of online uncertainty set estimation has long been studied, both in control and machine learning under various settings, under various names. And kind of the popular name for this is confidence interval estimation. And this is also very popular in machine learning. Here I'm listing a couple canonical approaches. And by far, the most popular approach that has been used to be combined with control algorithm is least square estimation, where you observe data, you use these data to use least square estimation to compute a point estimator, and then you build a ellipsoid confidence interval around this point estimator, and you treat that as your confidence interval. But today, I want to focus on a different estimation method called set membership estimation. So some of you may have heard of this, but I feel like a lot of us haven't heard about this. This is actually a very classical approach in control that dates back to the 80s and 70s. And this has been somewhat popular in subsets of online control, like robust adaptive model predictive control. And the reason why we care about this set membership is motivated by its empirical performance. So here I'm showing kind of in a scalar dynamical system estimation problem between set membership and least square. And so the first plot on the left is the diameter of uncertainty sets generated by the two methods from the exact same data. So as you can see, not only is set membership generating much smaller uncertainty sets, it's also converging faster than least square. And to the right-hand side are kind of the visualization of the uncertainty sets from the two methods. So the x-axis is the A parameter and the y-axis is the B parameter. So visually, it's just much bigger for least square than set membership. But this is only empirical. So this empirical observation motivated us to want to study set membership. And so that's the topic of this part of the talk. And let me describe to you what set membership actually does. So our setup is this linear dynamical system. We have A and B as our unknown system dynamical model. And our disturbance W is going to be assumed to be IID stochastic, coming from a distribution that has a bounded support. And the support is bounded between negative and positive capital W. And what set membership estimation does is to basically compute the set of all models that could have generated our data by combining themselves with a sequence of admissible disturbance. And so if you give me an AB and a corresponding admissible disturbance, and I see that my data could be computed using this A, B, and W, then this A and B would belong to PT. And pictorially, this is even easier to describe. So let's say we start with the initial uncertainty set P0, and we know our model lies somewhere there. At every time step, we see a transition data from xk uk to xk plus 1. This actually carves out an intersection of two parallel half spaces in particular. And what's left of this uncertainty set is exactly what the set membership computes. And in the next time step, we get new transition data. We get exactly 2 more half spaces, and what's left is a new PT, and so on. So this is what set membership computes. And in particular, anything instead of P2 is a model that could have generated X1, X2. Okay, so actually, so by the look of this, right, just by the way I presented it, the drawing of these sets, it looks like it should converge. Do they actually converge? They actually converge. So there's the set membership estimation PT that I'm presenting here is like the basic vanilla version of set membership. There's variations of it. There's even nonlinear generations of nonlinear generalizations for it. For different type of systems as well. And a lot of them do converge, and there's been a lot of studies on this. But even in this simplest setting for linear systems, linear time invariant systems, with this vanilla version, there's actually no study of how quickly PT actually converges. And for us to use set membership for learning-based control, especially for safety critical applications, it matters to us what the transient behavior is. Yes, Mohammed.
W is known, right?
This setting W is known, yes. In order to compute, yeah, good observation. Thank you. Yeah. So to compute PT, observe that we have to know what W is, right? That's how we have to compute PT. Right. So we don't know how quickly PT converges. So that's what we want to analyze. And towards this, we have our results, which says that under some technical assumptions, with high probability, the diameter of these uncertainty sets that are generated by set membership is going to converge like 1/T. And we get one transition sample per time step, right? So this is converging basically linearly. We have linear sample complexity. And so how does this fare against standard approaches? Well, least square actually converges like 1/√T. So this tells us that, at least in terms of time complexity or sample complexity, sample complexity, sorry, not time complexity. That's a different thing. Set membership actually converges much faster than least square. And this exactly matches what our teaser figure looks like, right? It's converging faster. It's also generating a smaller uncertainty sets. So that's great. What am I hiding under the rug for these technical assumptions? For those of you who's ever worked on anything about system identification, you will know that anything relating to these assumptions is going to suggest something about excitation, right? You have to have excitation about system. And indeed, the 2 major assumptions we will have is relating to excitation. So the first thing is that we need the disturbances to not only be IID stochastic, but it also has to have this condition where it hits the epsilon neighborhood of the boundary of the support of the distribution with probability that scales like scales linearly with epsilon. And so this big omega notation is basically saying that this function Q of epsilon, which is the probability as a function of epsilon, has to grow at least as fast as a linear function of epsilon. So what would be an example of a distribution that satisfies this? A simple thing would be a uniform distribution, right? So for any epsilon, the probability of a WT being realized to be something that is epsilon away from the boundary is exactly epsilon divided by 2W. What would be a distribution that does not satisfy this? That is, if our distribution is our bound W assumed bound in our computation for set membership is a very loose bound. So if the true distribution support is only bounded between W negative W, but we assume it's positive and negative 2W, then between that W and 2W, there's zero probability of hitting it. So then it won't satisfy this assumption. Okay, so the second assumption that we have is with at least some non-zero probability, the smallest the singular value for the data covariance matrix is bounded away from zero. This is basically to ensure persistent excitation with high probability. And a lot of the technical hurdles we have to do in this whole paper is to translate this high probability persistent excitation into high probability convergence in the diameter. So it turns out that there's a lot of work that you have to do to go from deterministic persistent excitation to high probability persistent excitation. If you're interested in this, I have more discussion on this.
Just a quick question, maybe you're gonna get to this, the state dimension. I noticed it's quite a bit worse with the set membership.
That's exactly the next slide.
Oh.
Yes, very good observation, right? So we're doing better sample complexity wise, but state dimension looks much worse. Set membership is, very much worse polynomial. Is it a fundamental challenge in set membership, or is it just an artifact in our proof? We don't know yet, but here's a simulation that suggests it may be actually an artifact of our analysis. Here's an autonomous system of dimension nx by nx, and we use basically the same amount of data for the system, and we grow the system dimension. We see how much the diameter grows as we grow the system, and we can see here that for two kind of canonical distributions, which is the uniform distribution and truncated Gaussian distribution, our growth looks about the same for least square for set membership. So we're hoping to improve and sharpen the bound, but there is some fundamental limitation in our analysis that we don't see a way to get rid of that polynomial. Yeah.
Here's a question real quick. So when you talk about least square, with what you're benchmarking all this to, least square techniques don't have to have bounded domains for W, right?
No, they don't.
So I mean, but you do have, you brought it back to confidence intervals in terms of least squares as well, right? I mean, you come up with a point estimation and then you have a certain confidence interval around that, which has to be prescribed, right? When I think of confidence intervals, I think, okay, well, that means you're just specifying a probability, like 95%.
95% probability, sure, yeah.
So that's hidden in here somewhere. There's
Yes.
also, the results are gonna vary depending on what that.
Yes,
that probability
absolutely.
is. Whereas set membership doesn't have that at all.
Yeah, it's a deterministic guarantee that your theta star is always there.
Make sure I understand. Okay.
Absolutely, yes. And it's to make it fair, right? So we set it to be like 75% confidence interval, which is a very kind of a low confidence interval. And it still looks much bigger than set membership is. But okay, soon you will see we'll have a fair comparison because there's a probabilistic version of set membership that we can have a fair comparison. All right. Okay, so we have a teaser figure before for dynamical system. We just want to make sure that it works also well and generalized to high dimensional system. So here's a Boeing 747 linear dynamical system. And then we see that the same observation we had actually generalized here, where set membership, again, it generates smaller uncertainty sets and makes it converge faster. But the thing is that we need to know the bound on the disturbances, right? And so what happens if we do not know the bound on disturbances? How much the algorithm deteriorates? What if we use 2 times W as our bound in the set membership? Well, it looks like it's deteriorating pretty fast. What about 3 times, 5 times, and even 10 times? It's actually performing pretty horribly. And this may partially explain why set membership hasn't been as popular as it should be, as we think it should be, because For the most part, you wouldn't know exactly what the tight bound is for your disturbances. And if you don't know a tight bound, you just overestimate it, it will perform really horribly. And least square almost always works, right? You can always get an answer. Okay, so how do we address this problem, right? That's our very natural next step. And towards this, we actually introduce an algorithm called upper confidence bound set membership, where our algorithm goes the following. We're going to first, based on the data, compute a lower bound on this unknown bound W. And this lower bound is called, we call this, we denote it as W bar of T. So what this W bar is, it's the magnitude of disturbance, the minimum amount of magnitude of disturbance that is necessary to generate the data you see. Basically, any sequence of disturbances that is smaller, strictly smaller than W bar is simply impossible. There does not exist an A and B that can be coupled with disturbance sequence that has magnitude strictly less than W bar that can generate what you see. This is the minimum amount of W you need. So this is the lower bound on W, capital W. And based on this lower bound, we're going to add onto it kind of a delta T to create an upper confidence bound for this unknown bound, capital W. So it's kind of like a sandwich situation. On the lower part, we have W bar. On the higher part, we have W hat. And we're going to sandwich this unknown bound W from upper and lower. Yes?
Is AB and P0 or is it P sub P capital T?
Can you?
Organization over AB, is it for AB and P0 or P capital T? I think P0. What is the set which we're looking at for the minimization?
This is yeah, in P0. Yeah, sure. You can do P0. Yeah. But you know, if you have, so with the assumption that I had in the previous slides, usually so basically after you can have some guarantee that after some steps it will be a bounded polynomial. So not super necessary that you have to start with a bounded polynomial. You can start with something really large but bounded to help with the computation, I guess. All right. So then we will just compute our set membership based on this upper confidence bound W hat and at every time steps, and hope that this W hat would converge back down on the upper side into the true unknown bound W. And towards this, our theorem actually says that we can find this delta T, this upper confidence bound additive component that scales like 1/T, such that with high probability, our true A and B is always going to lie instead of our set membership that's computed using the upper confidence bound, and that this upper confidence bound set membership uncertainty set still converges like 1/T, as it just like the same rate as if we know the bound. Okay, so where does it look? How does it look like in this entire plot? The pink line is what it looks like when we apply our upper confidence bound set membership. And you can see that it hangs about the same rate as set membership when we know the tight bound. There's a slight worse performance, of course, because in the beginning we actually we have this upper confidence bound that gives us some additional kind of looseness. Okay, so I'll stop here. If there's any questions, I'll take it here about this first part of the talk. Otherwise, I'll move on.
Can you comment a little bit on I mean, I'm thinking about like applying this to realistic problem. It's almost always going to be an output feedback type or an output. You're not going to have the state. You're just going to have measurements of output, and you have to fit A, B, C, not just A and B. How does that complicate things? Does it extend easily, or is it?
Very good question. We briefly thought about this. I think there could potentially be a way to just directly try to fit the Markov parameters of the system rather than directly fit A, B, C per se. Another thing is maybe it can be coupled with a state estimator rather than going straight for A, B, C, D. Very half-baked. Yeah. That would be a very natural next question, yes.
It just seems to me that that kind of also affects a little bit on how you talk about disturbance bounds, right?
Mhm.
Because you're assuming essentially a disturbance that enters directly into the state equation, you're bounding that. And what you really probably have in practice is a disturbance that multiplies by some matrix you don't know.
Hmm.
And that kind of affects that part of it as well, but it would just. So is that also something that kind of is extensible or?
I guess if you know, at least in the state feedback setting, right? If you assume W is pre-multiplied by a disturbance,
You just absorb it into the.
I guess you can absorb it somewhat into this, yeah, into the unknown bound, right? All right, so we just talked about set membership as an estimation method. Seems like it's a well-performing algorithm. How do we build a control algorithm on a set, right? Usually you do model-based control on a point estimator. So that's what I'm going to talk about next. And we'll study this algorithm or this framework through the problem of learning to stabilize unknown network systems under adversarial disturbances. So again, to motivate why we care about large-scale systems, energy systems are growing in scale and they're becoming cyber physical systems. So there's going to be a cyber layer on top of the physical layer, which means that you can allow communication between agents. This, of course, creates opportunities for communication between agents, and you can make control algorithms more adaptive and make them perform better. But it also can create more challenges because you have to deal with network issues and make them more robust to potential network failures in the communication layer. And so we'll model the network of agents as network linear systems. And I'll use the word network agent and subsystems kind of interchangeably for the rest of the talk. And for each subsystem, I will assume they're a linear dynamical system where the states locally are influenced by its neighboring system. And if you concatenate the state and contractions together, this is a canonical linear dynamical system, except that your A and B now have specific sparsity structure. And so again, we're going to assume A and B are unknown, so the whole network is unknown. And moreover, rather than now assuming that W is IID stochastic, like the previous part of the talk, and also commonly assumed in the literature, we're actually going to assume that now this disturbance is just bounded. It can be stochastic, but it doesn't have to be stochastic. It can be arbitrary, can be adaptive, can be omnipotent, and potentially adversarial. And on top of this, we're going to also endow this network with a communication layer, where assume that there is a communication delay between agents, and so each agent would actually receive differently delayed information and have to compute make their local decision with these differently delayed information. And moreover, because these networks can be very large scale, we don't want every agent to receive the global information and compute with the global information, compute with like the global information. We're going to restrict every agent to only compute with kind of local neighborhood of information. So there's like locality in our problem. So the problem is, how do we stabilize this whole unknown network system subject to local and delayed information for each agent? And how do we design a distributed algorithm for this? So there's really two challenges for this, and I'm going to separate it all a little bit because it's very difficult to talk about them together. So the first challenge is actually we have to understand how we can explore under adversarial disturbances. As I highlighted it before, right? So IID versus adversarial is actually quite different, and I'll quickly in the next few slides describe to you why this is very different for learning and control purposes. And the second challenge is, of course, the network constraints. And so today I will try to focus on the first challenge, where this is where I will introduce the uncertainty set-based learning plus control algorithmic framework. And for the second challenge, I will quickly touch upon a distributed control tool called system level synthesis. Okay, so again, to just quickly summarize our problem setup. let's forget about the network. This is kind of the global system. We have a linear dynamical system. AB is unknown. We make two assumptions. Disturbances are bounded but otherwise arbitrary. AB belongs to some initial uncertainty set that is large, compact, convex, controllable. And the very natural question for this is, why don't we just learn the model first and then apply control, right? After all, the first part of my talk is learn the uncertainty set, make it converge fast, and learn the model. Turns out that here, because we assume the disturbances are not IID stochastic, the adversarial disturbances can actually make exploration learning very difficult for control purposes. So here's a simple example. Let's say we have a scalar dynamical system here, and the only unknown parameter is A star. And A star is bounded between -10 and +10. So obviously, there does not exist a robust controller that can stabilize simultaneously everything in this range. And W is bounded by eta. And so our goal is to try to drive X into a safe range between negative and positive eta. If we had known A star perfectly, we would just choose our control action to be negative A star times XT, which will cancel the dynamics, and it will give us the closed loop dynamics to be XT plus 1 equals to WT, and this would satisfy our safety constraint. But if we do not A star, then we would have to use data we could use data to estimate A star as suggested by the previous slide and to compute a control action. However, now that WT can actually make us learn nothing about A star at all if eta is large enough by simply canceling our action in the dynamics. And we'll just be left with an observation that X is always 0 no matter what kind of control action we put into the system. So this is really bad news about learning or identification, because the state observation that we're always at 0 no matter what we do is not useful information at all for identification or learning purposes. But if you take a step back, this is great news for control, right? We want to be in this region that's centered around origin. And here, we don't care if we don't learn about the system. The adversary is actually helping us to stay stable or staying safe. So while this is a very contrived academic example, this is actually suggesting a very interesting exploration under the adversarial disturbance strategy, which is to try to force the potential adversary to either hide information but help with our stabilization goal, or to attack our goal of stabilization but have to reveal information about our uncertainty. And this is in direct contrast against a lot of the common approaches that tries to just first explore as much as we can about the system and then apply model-based control on it. And this also includes some common machine learning approaches, such as active learning, where you're just trying to actively learn something about the system and then try to control it. We are just trying to make the system stable, whatever it takes. Okay. So this online exploration, this is really just an online exploration versus exploitation balancing act. And this is, of course, not the first time the problem has been brought up. There's a long history, a rich history of dual and adaptive control that studies a similar problem, where we give simultaneous learning and control strategies for unknown dynamical systems. And while there are a lot of stability guarantees, I don't think there's any results on the type of adversarial modeling that we have here. And on the other hand, there's a whole community of online learning that explicitly does algorithms that trades off information performance in Markov decision processes. But there, stability isn't really a major concern. Usually it is assumed away explicitly or inexplicitly. But it does provide a lot of interesting ideas for learning against a potential adversary. And so in this talk, I'm going to combine ideas from both literature and to give stability guarantees for us to learn to control while dealing with potential adversary. And the main idea for the entire algorithm is basically to be lazy, which is to stick with a hypothesis model that could be wrong until we are proven wrong. And we're basically going to do exploitation through model selection. And hopefully when the model is proven wrong, we will gain information. And when the model is not proven wrong by the data, we will achieve stability somehow. So let me describe to you what the algorithm is. Again, we start with a large initial uncertainty set, P0. Our model lies somewhere there. Every time step, we will observe a data transition from the previous state control action to the new state, xt. And we'll carve out data, uncertainty sets using set membership. We get PT. And from PT, we're going to select a hypothesis model. And of course, how we select this hypothesis model matter, because based on this hypothesis model, theta hat, I'm going to use whatever model-based control design to design a control action. And this control action I designed is designed to stabilize theta hat, not theta star, right? So obviously it matters how I select theta hat. And once I select, I design a control action based on theta hat, I put this control action, feed it back into the system, and this whole process continues. I'll observe a new state, I'll use set membership, get a new uncertainty set, select a new model. Now, two things can happen when I observe a new data. First is this new data carves out a new uncertainty set that basically invalidates my previously selected hypothesis model, right? So at this moment, I know what I did before, what I selected before this theta hat 1, for example, in this picture is wrong. It's that wrong. So I'll have to select a new hypothesis model in the new set P. Or the new data actually could reveal that what I had done, what I had selected before, somehow remained inside of the new consistent set, which means somehow that I didn't do too bad of a job. Okay, so these are the only two things that can happen after I observe a new data. And these two observations is going to precisely tell us what we have to do in terms of model selection for exploitation. And I'll summarize what the observation is actually doing. So first of all, simple observation. Every time the selected model, hypothesis model theta hat is invalidated, obviously our model set must shrink, right? Because that's how you invalidate it. But because we have just verified that our selected model is wrong, the control action must have done something horribly wrong. Now, on the other hand, and this is a little more subtle, every time our selected model remained inside of the new set after new observation, we probably did not gain much knowledge, and most likely the set remained large. We don't know if this selected model, previously selected model, is correct or not. But what we can say for certain is that this control action that we computed based on theta hat t should appear to have generated a stable one-time transition. And here's an example to illustrate what I mean. So let's consider just this picture here. After observing x2 transition from x1 and u1, where u1 has explicitly been computed based on theta hat 1, we see that P2 still contains theta hat 1, right? So then we know this could be treated as if it had been generated by theta hat 1. Because theta hat 1 remained inside of the set. And so if we just focus on the scenario as if x2 had been generated by theta hat 1, and we see that u1 is designed to stabilize theta hat 1, it must mean that x2 would look like it's an exponentially stable transition. But of course, this would only happen when theta hat 1 is not invalidated. So the moment theta hat 1 is invalidated, this statement is no longer going to hold true. Okay, so summarizing, every time step, the selected model is invalidated, we gain information, obviously, but our control action is going to perform horribly. But every time step, our selected model remains inside or consistent. We probably did not gain information, but our control action is definitely going to perform well. And kind of going back to the contrived academic example I had, right? We don't care if we actually learn that much. We care whether we're performing good control actions or not. We're achieving our stability or not. And so observation really suggests that let us select models that will remain inside of any future yet to be observed consistent model sets or uncertainty sets. And I call this property of model selection consistency of the model selection, to be consistent with data. And basically, the more consistent we are with model selection, the less bad control actions we will take, right? Because we're only invalidated. We're only making a bad control action when we're invalidated. Okay, how do we formalize this notion of consistency? Here's how we do it. We're going to use total movement of the hypothesis model selection. And this is because in our algorithm, we only move our model selection when we're invalidated, right? So in the best case scenario, you select something in the beginning and you never move. Then you're basically always stable. You're always generating stable transitions. So you basically stabilize the system the entire time, right? That's the best case scenario. So the smaller this quantity theta t is, the better your overall system is going to perform. Now, this notion was first proposed by Dimitar Ho et al. In 2021, and it was applied to nonlinear dynamical systems for robotic systems. And basically, smaller quantity means less bad control actions. And we're going to select hypothesis model that minimize this quantity. And it turns out that kind of abstractly, this problem of given sequentially revealed convex sets and selecting points from these convex sets and trying to minimize the selection's movement is an abstract online learning problem called convex body chasing. And the whole problem is basically selecting points that minimizes the movement of the selection. And there's a lot of algorithms that actually solve this problem, have guarantees. And almost all of these algorithms has the intuition of trying to select models or points deep inside of the set. And they all have worst case movement guarantees where delta t is bounded no matter how long your t is. And translating into our problem setting is that no matter what the disturbance is doing and revealing and making your data look like, your total model movement selection is still going to be bounded no matter what. And so we're going to choose hypothesis data model use convex body chasing. And kind of our key technical contribution is to connect this delta t to closed loop stability. By the way, bounded delta t means kind of bounded state and control action. That's kind of how we translate it. Okay, and so we use CBC in this hypothesis selection part of this algorithmic framework. And I also intentionally left open what this model-based controller is. For different control objective, we can really plug and play different controller. If you want safety, you need something like model predictive controller to deal with constraints. For large-scale systems in this current problem setting, we'll use distributed controllers. And if you just care about stability, we will use LQR controller in the simplest setting. So if we just care about stability and we just plug in LQR controller, for example, this is the theorem you will get, which is to say that we have a worst case bound on the state and of course control action for the unknown system under adversarial disturbances. And the bound depends, of course, on the worst case system theoretical parameters of your initial uncertainty set. You have exponential decay properties that all stability guarantees have. And of course, your bound will depend on the worst case disturbance W that could potentially be persistent. And I just also want to mention, and I won't have time to go into it, that this whole algorithmic framework can be applied beyond the LTI system, linear time invariant systems. We have applied it to time varying systems because convex body chasing doesn't just have a version where it's nested convex body. It can also be arbitrary convex body in ambient space, so it can naturally be extended to deal with time varying systems. The control algorithm can be used to be used with MPCs so that we can do adaptive MPC to guarantee finite constraint violations during online learning and controlling. And we also have recently applied this algorithm to an HVAC control problem, where we actually deploy this algorithm for a highly nonlinear and high fidelity simulator called Energy Plus, which is developed by the Department of Energy. And it turns out that it just performs much, much better than a lot of the baseline reinforcement learning, transfer learning algorithms, and it's much more sample efficient. This is to appear in ACME Energy 2025, so stay tuned and happy to talk more offline. All right, so that's all I want to say about the whole algorithmic framework. Really, online learning helps with combined with the set membership uncertainty set helps us achieving these adversarial stabilization and control. And I'll really quickly touch upon this. Don't worry, there's not much more technical details to come up. So we have a network, right? And I just introduced to you what a single agent would do in this stability adversarial stability problem. A simple idea is to just let each agent run their own local copy of this algorithm. Why not? So if we kind of go through this process, every agent can, of course, look at their own local transition data, compute their own local uncertainty set using set membership, and run their own local copy of convex body chasing, all no problem. But the difficulty comes into play when we're trying to make these agents make control decisions locally with delayed information, but while still guaranteeing global stability, right? That's the difficulty. And so our key enabling tool is to kind of use system level synthesis, which is an emerging distributed control tools in the part for model-based control in this algorithm, so that we can make this whole algorithm distributed and guarantee stability. And just kind of and really the difficulty here isn't in learning anymore. It's actually in the control part. It's in the distributed control part, because even without any learning, having these communication delay and local information is a very difficult question for distributed control design, precisely because there are non-convex constraints for controller design. And so there's long and rich literature for distributed control to deal with these kind of non-convex constraints. And more recently, there has been a new tool that is called system level synthesis, or SLS for short, that can deal with the largest known set of non-convex information or network constraints. And essentially, it is just doing a smart reparameterization of your controller that turns all these non-convex constraints into convex constraints. That's what it's doing. And just to give you an idea what the parameterization is, it's actually very simple. So rather than designing for a controller, which again, right, that if you want network constraints, it's non-convexing these controllers, we talk about the closed loop mappings induced by a particular controller. So we don't design for controller, we design for the closed loop behavior induced by whatever controller. And so we first talk about what is the closed loop mappings phi x, phi u that we want, and then we find a corresponding controller that would achieve these closed loop behavior. And all these non-convex constraints on controllers turns out to be convex constraints on phi x and phi u, which are the closed loop mappings. So these are the SLS reparameterization. And that's all I'm going to say about SLS without going into details. I have backup slides if you want to know more details. The technical hurdles we have to go through is to analyze kind of the perturbation analysis of this SLS controller, like how sensitive it is to delayed information. How do we characterize kind of the delayed information, the error caused from delayed information locally into the entire global network, and know that it's not going to propagate and grow unbounded. That's really what we have to do. And the result looks very similar to the centralized case, except now our constant is going to depend on network properties. In particular, it's actually not going to depend on the global network sizes or global network delays. It's actually going to depend on kind of local neighborhoods and local neighborhood delays, precisely because we allow our system to only use local information and not the entire global network information. And that's all I'm going to say about this problem. So we introduced this learning-based uncertainty set-based learning to control algorithm, instantiated for this network control problem, see why it's potentially interesting, and there's a lot of use for it. And finally, how does it actually look like in a real system? Everything's linear I've talked about so far, right? So a very natural question is, what if I apply it to high fidelity simulators? What if I apply to nonlinear systems? Does everything break apart? Luckily for us, it did not. And so this is a quick application for voltage control in unknown grid topology. Again, this is coming back to the beginning of the motivation of the talk, which is the distribution grid can change its topology quite often, and sometimes we don't know its topology. And so how do we learn to stabilize a distribution grid without knowing the topology? And so we're going to assume we don't know the topology or the line impedance, but we also are going to assume that the actuation is limited. So this is kind of like a safety control problem. You have actuation limitation. And we're actually working with real data here. So this is a single phase Southern California Edison 56 bus network with 24 hours of real data. And rather than showing this kind of ugly-ish looking bulky thing, I'm going to use a equivalent representation on the right-hand side. So voltage 101, the whole goal of voltage control for distribution network is to inject power in each bus or node so that the voltages at each bus is maintained within some certain ranges. And here I'm plotting the 8 voltage profiles for 8 buses where the color corresponds to the nodes on the left-hand side. All right, so existing methods are insufficient. General approaches, there are 2 general approaches. First is, of course, identification plus control. Turns out that if you identify even just a little bit differently, like a couple nodes, child nodes are different, or some parameters are different, you can still violate a lot for your final control algorithm. And another approach is actually entirely network agnostic, but these algorithms, while they have safety guarantees, they actually cannot deal with actuation limit, which is like a key thing that you have to deal with in reality. You cannot assume you can inject infinite power in the system. So how do we actually fare in this type of system? So on nonlinear AC dynamics, we can deal with voltage violation very well. And as you can see, in the beginning, we had a violation because we need to learn. But once we learn and made a violation, we very quickly converge and do very well in terms of voltage safety. And beyond the hood, it's just the first rigorous guarantee on finite number of voltage violations by combining convex body chasing with MPC algorithms. We did not stop there. What if we do not know the bound on disturbances when we compute set membership? We use a similar algorithm as introduced in the beginning, the first part of the talk. Turns out that we're going to run into this. We have to, perform a little bit worse, but we can still guarantee safety. And what if we have prior knowledge, right? It's kind of unrealistic to assume that we have zero knowledge about anything. What if we know partial knowledge about who's a child node of who? It's very easy to embed these knowledge in the way we compute these set membership models. We instantly performs better. And that's all I'm going to say. And thank you for your attention and all the great questions.
Well, maybe time for one question.
Yes.
I'm curious about when you're choosing different models and rejecting your hypothesis, how can you kind of reject one hypothesis based on you only have one time point that is violating your
Right. So if you get in the data, right, it carves out things that are just impossible. Like it basically, once you get this data, it will carve out things that basically you will look at this data and you say, there doesn't exist admissible disturbances, any admissible disturbance that can be paired up with my previously selected model that could generate this data. So this model must be impossible, right? So I can carve it out. Does that answer your question?
I'm thinking about because there's kind of uncertainty at every time point. Would that just because some kind of super uncertain stuffs happen instead of like the model is not right? Because kind of like hypothesis testing is a hard question in statistics.
Of course, yes. I guess in our setting, we're just assuming that the disturbances, the model isn't known and that there's disturbance that could potentially mess with your observation. Yeah.
Oh, that's fine. I told you I was gonna cover them all before 4:30. So, let's take our speaker again and, talk to her. Yeah, we're gonna stop. Let me go. Yeah.
There's some similarities for what I wanted to.
Uh,
Abstract.
Burned out now, so. You know better being here.
That's true. The air is always good. Yeah.
That's freezing here.
Yeah. Adam Wheelman and John Doyle.
Okay. I was, I'll stop on it.